All right, okay, so thanks everyone for coming this afternoon. We're going to start Pierre's second lecture in a second, but there are, at the end, we got cut a little bit short, so if anyone has questions, and also Manju, if you're on the Zoom yet and you have a question, then some people, okay, so some people are saying they're feeling shy. Don't feel shy. Pierre is very receptive to questions. So Ulrich, can you, you turn it.
I'm not hearing you, sorry.
And okay, I can hear me, so I assume you can hear me. So you mentioned that there's quite a lot of models that you can generate as like level sets of some fields. So I guess in other parts of percolation, what you imagine doing is that in your vertices or bonds or whatever, you always hide the same type of field, namely just like IID uniforms, and then instead you create a model that possibly has dependence by choosing some rule for how to interpret the uniforms as some other variables. Say you, say this is what you do when you generate an FK model through exploration. So I was wondering, do you think that the models that you get as like level sets of explicitly like random fields with dependence are generally easier to track? Like, should it be easier to come up with exotic models that nonetheless we can analyze, or do you think it's sort of a wash?
So I'm not sure what a wash means. I also am not sure that I would qualify them as exotic. I mean, in some sense, if you think of the field as something you can change, then all of these models, so that includes Bernoulli on one end and the GFF on another, they're all part of the same family. And really, the fundamental object is the loop soup. And then it's really a question of, how many, like, do you only throw in small loops, or do you put in bigger loops, or do you, and you can do anything in between. So in some sense, I sort of rather view them all as part of the same family. And then if you want to go into sort of the FK or the easing kind of world, then in the spirit of loops, what you do is that you can still tinker with them in that you create interactions between loops. And there's of course one way to think about 5.4 is exactly in this way. So I sort of think that I like to think that they're all part of the same family, really. I don't think they're so disjoint. Yeah. So I hope that answers your question somewhat. Okay, should we start or?
Yeah, can you take one more quick question and then we start?
Sure, yeah.
Hello. So I'm trying to understand, so how much this power of R depends on the graph. So the question I have in mind is, suppose you have a sequence of graphs, which is for all of them, the power of R is same. And it is converging, say, in local weak convergence to some other graph. So for this converging graph, I mean the limit graph, will the same power of R hold?
Yeah, so if I understand your question correctly, I think what you're alluding to is that, of course, you can have this sort of, finite size version of this, which is you have a sequence of graphs, maybe even finite graphs, and their volume growth, follows asymptotically, say, some polynomial with a given exponent. And then, if you formulate the, natural finite volume analogs of these percolation questions, then you basically expect locally that the transition point where sort of a macroscopic component emerges is going to be described by exactly those critical parameters. So for instance, one thing that's probably familiar is if you have things like expanders, things that maybe converge in a local sense to things which are mean fields, so a regular tree or something like this. Then if you do GFF percolation on those, then you will get the mean field exponents, and in fact some of it is actually proved. So yeah. But even in low dimensions, you expect something similar.
All right, excellent. So thanks for doing the catch up for the question. And so
Yeah,
go
sure.
for it.
Okay, so so this was supposed to be a mini course, and I see many young people. So from here on, it's basically hands-on. So I didn't prepare slides. I'm going to write on my tablet, and hopefully that's going to work out well. Of course, the organizers had praised the merits of these, I don't know how many square meters of boards you guys have in front of you, and I regret that it's not on those boards that I'm writing, but I guess, yeah, you'll have to live with this. Okay, so the modest goal I have, it's sort of a minimal goal, and if I can do more, then that's even better, is so I flashed this theorem, which I'm going to quickly go back to, which tells you that at criticality for these models, the probability k is like r to the minus something. But you might have noticed that, I mean, one, of course, implicit statement is that the probability on the left-hand side goes to 0 at all. And if you translate this to the world of Bernoulli, this is the question of theta PC equals 0. And here, so of course, this is not Bernoulli percolation, but one feature that should already somehow catch your attention is that you're in dimensions strictly bigger than 2. So proving these things is actually not easy. And so the sort of minimal goal I want to show you is different ways you can actually show that this probability on the left-hand side goes to 0 and what sort of goes into that. And so, of course, refinement of these arguments then lead to the precise decay, but that's already that's not the first question. Okay, so towards this, let me now get started, and I hope I'll make this relatively self-contained. Okay, so just as a reminder, G is a graph. So I have put you guys on pins, so now I see the whole audience in front of me, which is a bit more pleasant than seeing my screen again, but I hope you can. So now I don't see if you can see what I write, but if you don't, then you just say something. Okay, so so let's assume that this is connected and locally finite, which means that every vertex has finitely many neighbors. And so on this graph, I have a random walk, which I called x. So this is, say, discrete time. And it has a law p sub x, and the little x here is the starting point. And so for today's lecture, I'm not going to assume anything other than that my walk is transient. So this is an assumption on G. Okay. And so I want to stress that, I mean, this is quite general, right? So you can think of regular lattices like, ZD. So of course, this is 2-dimensional. And if you want transients, then you should take dimension at least 3. You could also think of things which are sort of hyperbolic, right? So things like a regular tree or, variations thereof. And maybe another class of examples. So this is just to populate your imagination a little bit. You can also have things like, fractal graphs. So for instance, you take your favorite fractal, say this Sierpinski gasket here, and you sort of iterate this ad libitum, and you run a random walk. So you think of this, maybe you think of it as growing, in this way, and then you just run a random walk on the vertices of this graph. So it turns out that the Sierpinski gasket itself is actually recurrent, but if you give it a little thickness or if you replace it by a higher dimensional fractal, then it will be transient. Okay, so so here's your graph. It's transient, and that's all I'm going to need for today. Now, I want to introduce minimal amount of notation, so just bear with me for 2 minutes. So if you have a finite subset K of your vertex set, then so there are these quantities from potential theory that are sort of always appearing. So there's something which is called the equilibrium measure of K, which is a measure, but everything's discrete, so you don't really need to distinguish functions from measure. And so for probabilities, this is just the probability that the simple random walk started at x never returns to k again. So xn not in k for all n greater or equal to 1. whenever x is in k. Okay, so you have your set k, your equilibrium measure is supported on points x which are in k. Of course, if x is in the interior, then there is no way that after time 1 you're not in k, so it's really supported on the boundary. And then, it corresponds to the probability that the random walk never comes back. And of course, the walk being transient, this probability is positive. Okay, and then this measure has a total mass, which is called the capacity. So this is just a sum over the equilibrium measure over all the vertices. It's a finite sum, actually. Okay, and then you might remember there was something which I already introduced, which was the Green's function, g of xy. So this was the expected number of visits, which, so let me write it in this way. So I just commuted the two sums. And just to make it slightly more general, so I want to introduce the Green's function killed on k. So, when you kill on nothing, you get back your original Green's function, and killing on k means you only sum until you
Sorry,
my
could you
random.
repeat that? Your thing is just cutting out. Just maybe yeah, could you repeat that?
No.
Your headphones, because the writing wasn't cutting out and it was just the voice.
Okay. Hello.
Yeah, hello, that's better.
Yeah.
By the way, two comments. So is it possible to use a lighter shade of red? It's a little bit hard to read at the back.
Yeah, I'll try to avoid red. Yeah, sorry about that.
Perfect. And in the definition of the Green function, it should be xn equal y.
Yeah, sorry.
Thank you.
Thank you, yeah. Okay. So H, you can hear me, right?
Perfect.
Yeah. Okay, so HK was this entrance time in K. It's the first time you land in the set K. It's a stopping time for this random walk. Okay, so this is just a little bit of notation for my random walk. And so I want to state the Markov property. And I'm only going to state it at the level of this Green's function, which is going to be good enough for me. So here's a little lemma, if you like. Okay, so the lemma is that if you look at the probability that the random walk visits K, which, if you have access to this HK quantity, you can just write as HK being finite. So of course, this is not the probability one event when your graph is transient. Then actually, sorry, you can write this as a sum over y. Well, you don't need to, you can sum over everything, so let's not bother. It's a finite sum, g of xy times ek of y. Okay, and this is for any finite subset. So let me denote it by in this way, and any x and k. So if you're sort of analytically oriented, you might call this
u of x, if you like, and then all I'm writing here, if you apply, the Laplacian, so the generator of the walk, to both sides, then, what I'm telling you here is nothing but the fact that, u is the function which is actually equal to 1 on k, equal to 0 at infinity, and otherwise is harmonic outside of k. You can just, apply the Laplacian to both sides. Okay, so let's quickly prove this statement. So I'll copy it again, and I'll paste it to the next page. Yeah, you also learn a little bit of German, so not bad. Okay, so here's a proof. It's really a one-line proof. So why am I calling this the Markov property? So here's your set K. Okay, and the point X is anywhere, could be in K. So let me consider the case outside, but the other one works just as well. Okay, and now if I want to hit K, well, then, my random walk, which I'm drawing in yellow, it certainly has to enter K at some point, and then maybe it's going to, go to K, go back out, come back, and eventually it will visit K for the last time because the random walk is transient. And so I'm going to look at this sort of last visit point. So maybe let me call this point Y, and let me assume that this happens at time n. Okay, so if you sort of put this picture into formula, then you can decompose u of x. So you must hit k, so there has to be such an n, and there has to be such a y. So probability starting at x, at time n you want to be in y. Before then, you can do whatever you want. The fact that at time n you're in y already guarantees in particular that you will hit k, because y here is a point in k. And then, y was the last time I was, the point where I last visited k. So I guess you want xk not to be in k for any k greater or equal to n plus 1. It's just a partition of this event. And now you can just use the Markov property at time n. Okay, and so what does that give you? So it gives you a sum over n and y. Probability starting at x that xn is y. And now, you can restart a walk at y. And now you want to not be in k in the future. Okay, and this second quantity here, which actually doesn't depend on n, is exactly what I defined to be ek of y. So then, the sum over n gives you the Green's function, and that's the end of the proof. Okay, so since Trish told me to be pedagogical, I'm going to pause now. If you have any question, let me know. Okay, so this is a statement of the consequence, if you like, of the Markov property for the random walk, and we're going to use this formula several times.
Yeah, just we have one question. Okay, can you just show me how you defined h cap quickly, please?
Yes. Maybe I'll write it here. So it's the first time where a random walk is in k. It's what's called the entrance time in k. Okay, good. So so now I want to sort of translate this Markov property to a Markov property for the GFF. Okay, so first, maybe let me recall what the GFF was. So I have my transient graph, and I can define a Gaussian field on the vertices of this graph. So it's Gaussian. So, you know, it has mean 0. I won't write it again. And its covariances are given by this Green's function of the random walk.
Sorry, Pierre. Just one thing is, I think you're not assuming any regular degree, right? So,
Yes.
Is it symmetric without being scaled, or?
Yeah. So yeah, it is symmetric. I mean, my random walk is really. Yeah, so I'm hiding maybe one thing under the rug, but let me not go there. So
Okay.
maybe I should.
Yeah. No, that's fine.
So assume it's transitive. Otherwise, you should maybe normalize by the number of neighbors of y.
Okay.
And,
yeah, you are assuming transitive. Okay.
Yeah. But you don't have to. I mean, yeah. Okay. So good. Thank you. All right. I want to state the Markov property for the GFF, and so the question is, so I have still have my finite set K, and so what is the effect of conditioning on the free field restricted to K? And so the answer, so maybe I start drawing a little picture. Here's my set K. So let me define what's called the harmonic average. So I'll define it and then I'll comment. Okay, so this is something which is already mixing the random walk and the actual Gaussian free field. So it's actually a weighted average of Gaussian variables of these phi y's, but they get weighted by the probability starting from x that you hit K. And that you hit it in Y. Okay, so let's quickly look at what this is doing. So if you pick your point X inside of K, then, you know, of course, HK is just 0 and HX is just equal to phi X. So inside K, H and phi just coincide. But the interesting, you know, interest in this is when X is outside, and then you should think of basically, so inside of K, you know, you have your Gaussian free field, which is doing something. So this is what this is supposed to represent phi. Sorry, I used red again. My apologies. And then basically what HX does is it looks at the probability for a random walk, then it's going to say enter K through any particular point Y, and then it just takes, you know, the value of the field there. So it's a weighted average of the field on the boundary of Y, and the weighting is proportional to the probability starting from X that you will actually enter K through Y. And so in particular, since phi is a Gaussian field, this field H is also a Gaussian field because, you know, HX is a linear combination of Gaussian random variables. Okay, now you can state the Markov property for the field conveniently in the following way. So suppose that I define phi x to be hx plus psi x. So the way you should read this is I have defined hx, I have defined phi x, and so this actually defines psi. So again, everything here, all the three fields that I'm writing down are Gaussian fields because phi was to begin with, and I'm just doing linear combinations of stuff. And so the statement is, so first of all, the fields H and psi, they are independent. And so, of course, they're both Gaussians, that's clear. And moreover, the covariance of the psi field is actually the Green's function killed on K. And so you see in particular that's consistent. I mean, when psi x happens to be, if x is in K, then of course, GK is 0, and so psi is just 0, on K, which is sort of, which is clear since H is equal to phi there. So it's a sort of sanity check. Okay, so what this is telling you, the way you should read this is that if you look at, the law of phi, but condition on what happens in the set K, then you can write this, so it's, if you like, a regular version of the conditional probability as a average over psi alone. And what you do is you want psi plus H to just belong to whatever. So let's call this set A belongs to A. And here the P psi, only acts on psi. So this is a Gaussian free field killed on the set K. And the H here is, a measurable function of the stuff that you condition on. So you should think of this as a function of phi restricted to K. Okay. So that's, telling you that if you want to sample phi x over here, then you can basically write it as the sum of two independent components. One is this harmonic average that I wrote here, and the other one is just a Gaussian free field on the graph that basically has 0 boundary condition on the set K. Okay, now why am I calling this Markov property for the free field? Well, I'm calling it like this because it's actually a consequence of the Markov property for the random walk. So let's quickly, let's quickly see the proof of this. So I'm not going to prove everything, but I'll prove one thing and then I'll leave the other as an exercise. Okay, so let's prove this bit, the independence. And so let me consider a point X, which is any point in G, and Y, a point in K. Okay, so if I draw my little picture, here's my set K. My point Y is somewhere in K. Actually, it's enough if it's on the boundary of K, but it doesn't matter. And X is anywhere in G. Okay, and so I want to compute. So if I want to show that two Gaussian fields are independent, it's enough to show that they're uncorrelated. Again, just look at the characteristic functions. And so I want to look at maybe the correlation between psi x and phi y. So if I can show that this is 0, then basically I'm done. Why am I done? Well, so this is a statement between the independence of psi and h, but of course h you can write as a linear combination of points phi y where y ranges in k, because it's an average of such random variables. So just by linearity, if you replace phi y by hy, the conclusion will be the same. Okay, so we need to compute this, and hopefully this will be equal to 0. So of course you want to substitute for psi, which you can see at the top is just phi x minus hx. Okay, so if you do the expectation, so phi x, phi y gives you a Green's function, right? That's just a regular field. And then you have a minus sign, and then you have the expectation of hx times phi y. And then so if you unpack what this is, so the hx was a sum over z probability starting at x that you hit k, you hit it in z. Okay, and now let me move this up a little bit. So if I were to write phi z here, then this would just be the definition of hx. But now phi z, you have to compute the expectation against phi y, right? That's where the randomness is. And so this gives you an extra g of zy. Okay, now why is this quantity equal to 0? Well, simply because if you start your random walk at x and you want to, so maybe let me use a different color. Let's see, maybe green. So if you want to count the expected number of visits at y, and y is a point in k, then you better enter k. I mean, you have to. So you'll enter it through some point. Could be y or could be a different point. So maybe that's this point z. And of course, up until that point, you haven't missed out on your counting because you haven't actually hit y yet, because y is in k. And then, of course, the random walk might go to y, might go out, might come back, and eventually it will go away to infinity. But basically, what this decomposition tells you is that exactly if you want to compute g of xy, it's supposed to first look at where you enter k and then look at the expected number of visits starting from that point z where you enter k at y, which is this thing. And so by the Markov property, the two are equal to 0. So here technically I've used the Markov property for the random walk. And it's actually the strong Markov property at time hk, the entrance time in k. Okay, and that's the proof. So the other statement, the fact that psi has covariance gk is done similarly and follows by a similar decomposition. Okay, any questions about what I just said? Nope. Okay. So now I need to organize myself a little bit. So since the organizers threw me some curveballs and I have to finish at 5 past the hour, so yeah, when am I supposed to?
No, you don't need to finish at 5 past the hour. I mean, we started a bit late, so yeah.
Yeah. So can you give me a fourchette? Sorry, a window. When do you want me to stop?
What window do you want? Do you want to do like 3? We started 10 minutes late again, I think. So 3:15?
Yeah, that's perfect. Yeah.
Yeah, okay, cool.
Okay, so good. So now I want to start to study percolation for the GFF. And so to do this, I'm going to consider excursion sets. So I look at the point where the field is greater or equal to A. So this is not exactly the percolation model I talked about in the first hour. It's maybe a simpler one, a more naive one. And this is, so this, was first studied by Brickmont, Lebowitz, and Mess in the 80s, and then it sort of lay dormant. And Snitman was really the one who sort of brought it back into the game because it's actually, closely related to another model, which is called interlacements. And then it, was sort of repopularized, and it was looked at by various people, including myself and many others, including, of course, Subhajit and Franco, so various people who are in the audience. Okay, so so I want to study this simpler model for now because it actually already allows for some conclusions which are even going to be useful for this other model that I was talking about before. So if I want to do this, so let me fix a reference point in my graph. Let's call it 0. And A here is a real number that can vary. Okay, and so the theorem, so this is not the way Brickmont, Lebowitz, and Mess stated it, but I'm going to state it this way. So actually, I mean, let me stress here, you really only need the graph G to be transient, so it's completely agnostic to the geometry. And let's say A is positive for now. So if you look at the probability that K is disconnected from infinity, so K here is any finite subset. So you look at this above level minus A. So let me just make sure we understand each other. So U connected to V above A means there is a path connecting U and V along which, a path that lies in this excursion set, so along which phi is bigger than A. And if I write a little disconnection like this, then it's just the complement of the connection event. So this event that I wrote here is that there is no unbounded path that starts from K and along which the field is greater than any negative number. Okay, so this probability is actually bounded by e to the minus a squared over 2 times the capacity of K. And this is true on any transient graph. The capacity I introduced a couple of slides ago as the total mass of the equilibrium measure. Okay, and so so corollary of this is the following. So you can, now introduce the critical parameter for this model. So let's say I introduce my order parameter. I'm going to call it theta of A. So this is the probability that my reference point 0 lies in an infinite cluster of this excursion set. So mind you that this is decreasing in A. Okay, and then there is a corresponding critical point, plays the same role as PC, but now it's a real number instead. So this would be the infimum over A, such that theta of A is 0. Okay, these are just definitions. The corollary, I guess, comes now. And the corollary is that AC has to be greater or equal to 0. So this is a Keston type result, if you like. I mean, this is a statement that PC is at most a half. If you have density strictly larger than a half, then you percolate. Okay, and so first, why is this? So if you look at the theorem, so this is the proof of the corollary, I guess. Okay, so there's various ways you could approach this. You could take K, a big box, and let it grow, but actually that's maybe not the best thing to do. So let's just take K to be, our single point, and then the probability that 0 is not connected to infinity. So what you have here on the left-hand side is, 1 minus theta of minus A. This is probability that 0 is not connected to infinity. Okay, so by the theorem, this is bounded by e to the minus a squared over 2 times the capacity of 0. And so what's the capacity of 0? Well, this is just 1 over g of 0, 0, right? Because if you go back to my little first lemma over here and you pick k equals 0 and x equals 0, then of course the left-hand side is 1. And then the right-hand side is just g of 0, 0 times the equilibrium measure at 0. But this is also the capacity on 1-point sets. So the capacity for the set is just the Green's function at 0, 0. And my graph is transient. So this Green's function is finite, which means that this quantity is actually strictly positive. And so, this is, after all, strictly less than 1 as soon as A is positive. And that's the proof of the corollary. Okay, so I want to draw your attention to the fact that, this is, you should appreciate this. And I see a few faces of people who've been in my course this past term, so of course they've heard this already. But so, in higher dimensions, it's not easy to create things which percolate. And here, what I'm telling you is that actually, if you use the GFF, you have a structure, it's excursion sets, and they percolate at any density which exceeds 1/2. So it's not even a perturbative result. You see, for instance, in Bernoulli percolation, when you just want to show the existence of a supercritical phase, usually you do a Piles argument or something like that. And you can do something like that here as well, but this is a much more, much stronger statement because there's already percolation close to density half. And so let me just mention in passing that, you know, there's various works. So I'm thinking, for instance, about work by Goswami, Severo, and Duminil and co-authors, where, you know, they prove PC less than 1, so the existence of a supercritical phase for Bernoulli using the GFF. And so fundamentally, the percolating structure that they use is exactly this GFF at levels, say at level -1 or something like that. Okay, so I wanted to prove this corollary, and maybe we'll just have enough time to do it. It's not very long, but it's, I think, quite pretty. Okay, so we want to prove this disconnection statement. And if you indulge me, I'm going to, sorry, I'm gonna pack K inside of a finite set V, and it's actually enough to prove this statement. So what I'm claiming is that the same bound holds uniformly for V containing K, and then, you know, if you can prove this, then you can let, you know, V exhaust all of your graph, and you get the statement. So now I've, you know, pulled myself back to sort of a finite volume statement. Okay, and so now in percolation, and this is going to be a theme basically for all the lectures, one thing that people like to do is they want to use exploration. So, you know, if you don't know this paper, if you have nothing to do tonight, then I can recommend, you know, there's this paper by Hugo Duminil and Vincent Tassion, you know, it's called New Proof of Sharpness, and they even wrote it in a version only for Bernoulli percolation on ZD. It's just a few pages, it's not a long argument. And so this is sort of the, you know, the simplest proof of sharpness for Bernoulli that we have. And you can see in the proof that there is sort of an interplay between clusters being, you know, explored from inside, from a point, and from the boundary of a box. And here it's much the same. So there's lots of leverage that can be gained from exploring either from inside or from outside. And somehow the thing that, you know, makes all the difference for the GFF is that you have this Markov property, which in a way allows you to make this exploration even more precise than for Bernoulli. Okay, so in the proof of the theorem that I wrote here, you're already going to see one of these two explorations, and you're going to see the other one in I guess in the next lecture. And here the game is actually to explore from outside. So you will explore things from the boundary of this set V. Okay, so more precisely, so here's a proof. So let me try and draw a picture. So this is my set K. This is maybe my reference set V. So this is the boundary of V. So you should think of V as becoming large. And so what you want to explore is maybe something you could call C max. And so this is sort of the outermost you know, blocking interface inside of V. So what do I mean precisely by this? So if I try to stick with my coloring, you know, blue being open and red closed, so you explore all the open clusters of the boundary. So you explore, you know, you reveal every vertex of the boundary, and you know, if phi is greater or equal to -a, you keep on exploring inside, and at some point you will stop. So maybe all these vertices, so red,
They're red.
sorry, this is my color code, which is why I'm using red. You know, at some point you will reach the boundary of your clusters, and everything you will find will be red. Right? Because of course, if you want to explore an open cluster, you need to do it until you figure out that you're no longer in this cluster, and this will be when you first discover closed vertices. And so the event that there could be more, red stuff surrounding the set K, but the event that K is not connected to the boundary of V by a blue pass is really the event that if I explore these blue clusters from the boundary, none of them is actually going to go intersect K. That would be the complement event where you have a connection. Okay, so now let's try to exploit this Cmax. So Cmax is all the explored region that I have obtained, and the way that you can exploit it is in the following way. So let me look at some local observable inside of K. So what I'm going to look at is the average. You don't need to make this choice, but it is in a sense an optimal choice. So let me explain what I'm writing here. So EK is just a probability measure. It's the normalized equilibrium measure of K. So it's equilibrium measure divided by capacity. It's something which is supported on K. And EK phi just means average the field according to this equilibrium measure. So I do a little average of phi inside of K. You might ask, why do you choose the normalized equilibrium measure? Well, you could also choose the uniform measure. The argument would also work, or you can even take a point that you're going to get an upper bound, but somehow, in a sense, the best bound you can get is by choosing this equilibrium measure, and I'll come back to that in the next lecture. So for now, just work with me. Okay, so this is certainly bounded from below by the probability that same event, and I have my disconnection. So let's call it dkv. So this is the event that K is not connected, sorry, to the boundary of V. It's the event you see in this picture. Okay, and so of course now if I use my exploration, I can rewrite this by decomposing according to this outermost blocking surface that I explore. So everything's discrete, so it's going to have some realization C. So there's a probability that less than minus A, and that C max is equal to C. Okay, and so now, of course, the thing to note here, so this is the first important bit, is that, and that's the whole point of an exploration argument, is that this part here is actually measurable with respect to only the field restricted to C, right? If I explore this blue and red stuff coming from outside, I don't need to reveal, what is in this region here. Okay, and so good. So now you can use the Markov.
It's a disconnection event, or I can't see whether.
Yeah, sorry. Thank you. Yes. So the event corresponds to the picture that you see at the top. Okay, so here I still have my field phi, and what I'm going to do now is that I'm going to write phi using the Markov property as psi plus h. So remember, when you do that, right, this depends on a choice of the region you condition on, and I want to condition on the region C. So I'm using this with K in my previous notation being equal to C. Okay, so if you go back to what I was writing before, I'm doing this harmonic decomposition that you see here, and I'm conditioning on the field restricted to C. Okay, so if you do that, of course, there is going to be this bit over here, h, which is actually going to be a function of these random variables, and there's going to be this psi here, which is completely independent of this stuff. So now, if I just use independence, so of course independence plus the Markov property for my field in the way I've explained it here, then I can get a lower bound by just saying, okay, if I want the average here to be at most A, I can write that the average with psi should be, say, less than 0. And I keep all the stuff that depends on phi restricted to C. So this is, of course, all dependent. Okay, and once you're there, so here I've used, of course, that maybe you should read this backwards, that these two together, right? If you sum these two events, psi plus h gives you phi, and so the sum will be less than minus a. Okay, so this thing here, I'm running out of space. You know what? I'm going to give myself a little bit of space because otherwise it's just going to be... We're almost done. Yeah. Okay, so this was my last expression. So this here is just a Gaussian random variable, and it's not degenerate. That's easy to show. So that probability is actually just equal to a half. And now the thing to notice is that I claim that you can, basically rid yourself of this event altogether. And the reason is that, so this is now where you use the GFF. Remember that, this this here, if you write it out, is just some average over h. And the important thing is that x here is a point in K. But if I go back to my picture, so here's my x. If I want to evaluate hx, remember this was just some weighted average. Actually, the weight is according to the probability that the walk will hit this red hypersurface in a particular point, and it's going to be an average of phi on this red surface. But on the red stuff, phi is less than minus a. So, if I do an average of them, this is still automatically less than minus a. So this comes for free, so to speak, and then you can basically sum the the decomposition of your disconnection event back into itself. So this is bigger than whatever, 2 to the minus 1 times the probability of this disconnection event. So now you read all of this backwards. You have an upper bound on the disconnection event, which is simply given by some deviation estimate for a Gaussian random variable. So now all you need to do is apply just a standard Gaussian estimate for this Gaussian random variable. So just apply something like a probability that x, which is mean 0 with variance g is bigger than t is positive, is bounded by so 1/2 e to the minus t squared over 2g. So here the 1/2 is a little bit important. Usually you see this maybe with a 1 over t or something like that, which is of course better when t starts to be large. But here t is a, and a can be arbitrarily close to 0. And the 1/2 is a lifesaver because there is a factor of 2 here when you go to the other side. So it will actually cancel this. Okay, and now, I mean, you want to apply this. So if you remember my statement, the bound was e to the minus a squared over 2 times the capacity of K, and all you need to observe. So in our case, X was this, average of Gaussian random variable. So we need to compute the variance G. So we need to compute this thing. This is the variance because it's centered. Okay, so what does this give you? So you get a double sum, right? You get EAX, EAY. It's normalized, so I need to divide by the capacity squared. And then, it's a GFF, so I get a Green's function. And so if you sum this up, so maybe you sum over y, you do this sum. Then by the lemma, I prove that the beginning, this is just the probability starting at x that you actually hit k. But, x being in k, this is just equal to 1. So the yellow stuff just goes away. Then, you sum EA of x over x. This gives you 1 capacity, and you have a capacity squared in the denominator. So this is just cap k inverse, right? Which sits here in the denominator, so it actually appears multiplicatively in this theorem. Okay, so bottom line is that you use the Markov property crucially at this step to basically say that this little local observable in K that you have built feels the exploration from outside, the influence from this cluster Cmax. Okay, and maybe this is a good time to stop.
Thank you, Pierre. Okay, so any questions from the in-persons or in the Zoom? Oh, you have a microphone? Okay.
I can't hear you, sorry.
You have to flick the switch.
Hello? Yes, good. Yes, it's a bit of a side question, but could you quickly remind what's the order, say, of the capacity of a box on ZD? Just to glimpse of what this would say. I'm sorry, it's a beginner question.
No, it's actually a good question. So this theorem actually applies, to any set K. So if you take, for instance, G equals ZD, K to be a box of radius n in your favorite norm, say in, really a box in an infinity norm, then actually the capacity grows like n to the d minus 2. Okay, and you can actually show that this upper bound here, so not its dependence on A, but its dependence on N when you take K to be a large box, is actually sharp on ZD. So for this you need a corresponding lower bound, but you can actually prove that. And so this tells you, for instance, that this is a first instance of where things are very different from Bernoulli, because in Bernoulli, if you are deep in the supercritical phase, then, to disconnect the box, you basically need to close the surface around it, and the cost for this is exponential in n to the d minus 1. So here it's much less costly to actually disconnect, and this has to do with this tension that I was mentioning. So, when you start to have a little region where maybe you push the field below -A, then actually it helps also around it to to do the same, and that's in some sense why the cost is less than if everything were completely independent, because there, even if you do something locally, it doesn't really help anywhere else. Yeah.
Questions? Oh, yeah, go for it.
Thank you. Okay, thank you for the explanation. So, my question is it difficult to get a lower bound, and I mean, in your answer, do you suggest a method for doing it, a sort of coarse graining, and you analyze different regions, or is it more difficult than this?
Can you hear me?
Yes.
Okay. So for the lower bound is actually, you can just come up with a strategy and try to get a lower bound like this. So in Bernoulli, the strategy would just be close all the vertices on the boundary of the box, which is gives you the right order of magnitude. So here, the one way you can argue is to basically say, okay, you can. So you are super critical in a sense. So you want to implement a low probability event. One thing you can do, and that's actually the proof, so you can shift the level A so that you become subcritical. And then this connection becomes a likely event. It's a probability 1 event, essentially. So if you do that, when I say you shift the field, so there is a way to implement this for Gaussian fields, which is basically using, completing the square, or more scientifically using Cameron-Martin or something like that. And when you shift, basically the cost, the exponential term that you pick up is essentially the cost from shifting the field, which is an entropy. And it turns out that, or a quadratic variation, if you like, and it turns out that, you can of course shift the field in good and bad ways. So a bad way to shift would be to shift to a subcritical level, say in the set K, and everywhere outside not to shift any at all. If you do that, then you're going to create very large gradients, on the boundary, and you're going to get again a lower bound, probably of the order into the d-1. But you can do something a little bit better, which is that you basically shift to whatever level is going to be subcritical in the box, and then outside of it, you sort of let it linearly go to 0. And actually, linear is an optimal choice up to. I mean, the very best choice would be to do it harmonically, but linear will already do it, and linear has the advantage of making the gradient smaller, right? So you imagine that you have like this, this ancient pyramid with the staircase outside, and so if you use this shifting, then in your Cameron-Martin term, you're going to pick up essentially this capacity as a cost. Yeah.
Okay, any other questions? What about the online? Is there anything? Does anyone have, can someone just check whether there are online questions? Everyone's connected. Maybe, okay. I guess that's a no. I mean, if you're online, you can speak. It's yeah. Okay, I think that's it. So let's thank Pierre. I have like one admin thing before we all go. So Pierre, I think I told you we would start at 11:30 tomorrow, but would you like to start at 2:15 Indian time instead? You don't have to wake up at 6, and then you do a double session 2:15 to 4.
Yeah, that works.
Okay, excellent. So then the schedule that we have on the website is correct. So we start tomorrow at 9:15 with Dima Chalkak. Great. So
yeah,
all right, thanks again,
Dima. Thanks, Dima, for allowing me to sleep longer.
He says it's my pleasure. I don't think he hear about the microphone, but he said you set too high a standard. But thank you for the beautiful lecture, and thanks for like for giving it online at, I know, an ungodly hour in the morning. But
Yeah.
excellent. Thanks.
My pleasure. Okay, bye.